Well, so let me start from some reminder. So as usual, G is a finite group. And G hat is what is called the dual object. Dual object, which means that this is the set of equivalence classes of irreducible representations. And this is a finite set, as will be seen from the theorem that I will recall in a minute. So, my notation reg tilde is the biregular representation on the set, on the space of functions on our group. And I recall its definition. So if you take a couple of elements, so G1, G2, this is a couple of elements, which is an element of a double G. Some questions? Okay. And then we define the biregular representation as follows. If we apply this operator to a function f and evaluate at h, and by definition this is as follows: h, G1, G2 inverse. One can interchange G1 and G2, and this gives the same representation up to equivalence. And I recall the result, fundamental result, which says that this representation is equivalent to the direct sum of over irreducibles of representations of a double group, exterior tensor products, T and T bar, which means the dual representation. And this is proved by constructing explicitly a map, which I denoted by star, the direct sum of the matrix spaces, the spaces of operators on our representation spaces over T and G hat to the space of functions, which is a linear isomorphism and also an isometry with respect to a scalar product, and also an intertwining operator, because we have an action of this group on each of these spaces, and hence on the whole direct sum, and the same group also operates here. So, and a corollary which is deduced from this corollary is as follows. Let's consider a set of irreducible characters. Irreducible characters, which means that T ranges of the dual object, and we take their characters, and these are an orthonormal basis in the space of class functions, in the subspace of class functions into the space of all functions. And moreover, so this means that if T is not equivalent to T prime, T and T prime are
Понятно? Ладно, это частно, потому что мы типа обобщаем.
Okay, so this implies that the characters are orthogonal and an irreducible characters is orthonormal, has squared norm equal to 1. So this is my reminder. Let's develop a little bit these results. Let me introduce what is called the representation ring. Ring. What is this? So we take a lattice, one can say a lattice. So by definition, rep G is the direct sum of a billion group Z of integers. So this is just a formal definition. So we take, which is equivalent to a billion group, which take the direct sum of a certain number of copies, and the number of copies is the cardinality of a dual object. So this is a Z module. And next we turn it into a ring. Turn it into a ring. And for this, we need to define a multiplication. And multiplication is defined on the basis elements. So the multiplication is defined by tensor multiplication of representations. So we take, say, let's identify the irreducible representations with the basis element in this lattice. And we have a notion of a tensor product. So we tensor to representation and can write it as a direct sum. Direct sum, maybe it's better to put here prime and double prime, and then the sum is over irreducibles, and some constant, which depend on all three objects. These are certain non-negative integers. So what I write here is just the decomposition of this representation into a direct sum, of irreducible with certain multiplicities. These are multiplicities. And by the very definition, we take these multiplicities as the structure constants in this ring. So these are taken as structure constants of product in the ring. So it's easy immediately. It's immediate to check that all is all right. So it's indeed an associative ring. So elements of this ring what are elements of this ring? These are formal Z-linear combinations of irreducible representations. If all the coefficients are non-negative, then these are true representations, but otherwise these are what is called virtual representations. So the situations is just similar to the construction of integers from the natural numbers. We take formal difference of natural numbers and we get a ring of all integers. So this is essentially the same, only the multiplication is not the usual multiplication of integers, but it is determined by the tensor product of representations. So maybe if there are some questions, so please ask. It's okay. Well, so what is this ring? And the idea is the following result, which is well, there is an isomorphism between this representation ring and one can take the z-linear combination. Take the z-linear combination of irreducible characters. And this is essentially the same. Why? Because direct sum corresponds to some characters. And we know that a character determines the corresponding representation uniquely up to equivalence. And we also know that the irreducible characters are linear independent. So this correspondence is 1-to-1. And next, the tensor product here, precisely corresponds to pointwise product of characters as functions. This is because if we take the tensor product of two operators, then the trace of a tensor product is the product of the traces. So, excuse me, there are some questions. What are questions? The negative gives virtual, right? Virtual, yes, exactly. Exactly. So what is the idea? The idea is that many questions about representations can be reduced to the level of characters. Not all, of course, but many questions. And dealing with characters is, in many respects, simpler than dealing with representation, because a representation is in some sense, a complicated object, some operator valued function on a group. But a character is simply a function. So this is a simple but very important device, simply because, I repeat, characters are simpler objects as compared with characters. Here is some example. Why this correspondence is useful. So if you have two representations, T and T prime, two representations. And I recall that this quantity, mu T prime, is the dimension of the space of intertwiners. Intertwining operators from one space to another space. But in terms of characters, this same number is nothing else than the scalar product with respect to the canonical inner product in the space of functions. And so in particular, if T prime is arbitrary and T is irreducible, then the multiplicity of T in the decomposition of T prime is equal to this scalar product. And for instance, take as T prime the one-sided regular representation. One-sided regular representation. Its character. So we take T prime, the regular representation, right or left, no difference, because they are equivalent. And then the character of this representation is a delta function. A delta function on the group G, which is by the very definition. So this means that the value at element G is equal to 0 if G is not the unit, and 1 if G is equal to this one. And immediately we get that the scalar product is equal to the dimension of T, which means that the decomposition of a regular representation comprises all irreducible representations with multiplicity equal to the dimensions. So this is just a simple application. Some questions maybe, so please ask you. Well, now I want to discuss the notion of the group algebra. group. You probably already know this, but let me discuss in some detail what is this. A very definition. The elements subject are formal. Formal.
Извините, пожалуйста, я
Да.
вот немного не понял по поводу того, что у вас характер регулярного представления равен единичке, если вы берете тождественный элемент. Он разве не равен размерности? Или характер
Размерности чего?
вашего пространства, вот этого векторного пространства? Я просто не понял, сейчас, ну, если вы просто поясните, почему это единичка, я пойму, наверное. Я просто запутался.
Ну, давайте мы с вами сейчас разберем этот момент. Вот у нас есть пространство, да? Так.
Ну да, да.
Yes. Характер. Ну да. Это глупость, конечно, да. Я что-то тоже почувствовал, что тут какая-то мура. Вот идет мура, да, извините меня. Ну да. Да, вы правы. Я чувствовал, что я вру.
Тогда еще, наверное, сейчас... почему это 0? Это...
Ну, почему 0, это-то понятно, потому что если элемент... Сейчас, подождите. Ну да, почему 0? Ну, просто любой базисный элемент, он сдвигается. Если у вас элемент не единичный, то он двигает любой базисный элемент. И поэтому...
да, извините, правильно, спасибо.
Вот. Да. Спасибо, что вы меня поправили, да. Это вранье было, да. Окей. So...
Sir, why is it cardinality of G when G is equal to E? I am asking why is it cardinality of G when G is equal to E, the delta function?
It's not delta function. I'm sorry. It's yes, you are right. Okay. So elements of a group algebra are formal linear combinations.
А можете напомнить, почему это характер регулярного представления равно размерности G, ну, мощности G?
Ну, смотрите, если у нас, нам нужно взять след элемента, да, что у нас единицы, вообще всегда характер в любом представлении, значение характера в единичном элементе равно размерности. Это единичный оператор. Единичный элемент переходит в единичный оператор. Его след равен размерности. Тут уж никуда не денешься.
Спасибо.
Это я тут в 3 соснах, как говорится, заблудился. Прошу прощения. So we take formal linear combinations of the group. So write it as follows. A is a formal linear combination with some complex coefficients. let's write as follows. So these are the group elements, but let's represent them by these symbols. This, okay. And the product, so this is a complex space by the very definition, and the product is induced by the group law so we have multiplication which is defined on the basis. These are the basis elements, and we know how to multiply them using the group structure, and hence we we extend this product to the linear combinations. So let me discuss a little bit how to understand. So how to understand these elements. It's tempting to regard them, so are the functions. So an answer probably is yes, because we can treat these elements, we can identify them with these coefficients, with these collections of coefficients, and they are functions. So usually people say, yes, we take functions on the group and and convert and turn this space of functions into an algebra in a natural way. This is true, but not exactly. Why? Why I think it's not exactly? Because actually, one must think sense of the group algebra is of measures, not functions. Why? The reason is follows. By functoriality, these are different objects. By measures here, I mean not necessarily positive measures, but sign measures and even complex value. So let's, I would like to propose a little discussion. So assume X is a finite set, it's a finite set. Then we have two spaces, two linear space in duality. So we have a space of functions, X, and we have a dual space, a space of measures. And these two objects are in duality. Measures are dual to functions. There is a pairing, natural pairing between functions, measures, C. And note that if you have a map between two finite sets, when we have the space of functions are mapped in the reverse direction, and measures are mapped in the same direction. Maybe it's better to, I'm sorry, maybe it's better to slightly change this notation, just to emphasize the difference. And from this viewpoint, one can explain why the elements of a group algebra are measures and not functions. Why? Because if we look, as a space of measures. And then what we have? We have a map G cross G to G. It induces the map measures. And for finite set, this is the same as the tensor product. So this is exactly the definition of the product on the space of measures. This is the product. And the space of functions, has a coproduct, product structure, because we have the same map here, a multiplication map, induces arrows in the reverse direction. So this is a coproduct. So this is important. Sorry, there are some message. Sorry, what is this? Oh, well, this is okay, I will explain this maybe later in the end, but you should know this. You should know this. I'm sorry, but you should know the fact. The functions are mapped in one direction, and measures which are dual to functions are mapped in a different direction. So, well, the next topic I would like to discuss is the following. There is a one-to-one correspondence between, say, representations of G, always finite dimensional, and non-degenerate representations of the group algebra. Non-degenerate means that formally one can think about a zero representation of an algebra. The whole algebra is mapped to zero. And to avoid this bad situation, we say that a representation of an algebra, in our case, it's a unital algebra. It has a unit. So non-degenerate means that the unity is mapped to the unity as an operator. And there is a one-to-one correspondence. So it's easy to see, an easy exercise.
Извините, а можно спросить,
Да,
что
пожалуйста.
такое представление групповой алгебры? Это то же самое, что представление группы? Или...
Нет, подождите, у нас есть групповая алгебра, у нас есть, это алгебра. И можно говорить о представлениях алгебры. Это значит морфизм алгебры в пространство операторов, сохраняющую структуру сложения, умножения, на скаляры, умножение в самой алгебре. Ну, еще мы хотим, чтобы единица переходила в единицу, чтобы она в ноль не перешла.
Спасибо.
Алгебры. Ну, и тогда, если у нас есть представление группы, то мы получаем представление алгебры. И наоборот, имея невырожденное представление алгебры, мы сужаем его на группу, а группа содержится в этой алгебре. Групповые элементы просто являются элементами алгебры, вот эти дельта G. Мы получаем тогда представление группы. And moreover, we have unitary, if you have unitary representations, and we know that essentially all representations are unitary with respect to a suitable scalar product, so we can think about unitary representations only. So unitary representations of G, this is the same, essentially the same as non-degenerate as above, and star representations of what means star representation? This means that we have an involution in algebra. There is an involution. This involution. This is an anti-isomorphism, which means that the order of multiplication is reversed. It's also is antilinear. And the definition is as follows. If A is the formal sum as above, then A star is the formal sum of what? A of G and this one. And a representation of an involutive algebra, so this object, A algebra and involution. And if you, such a couple is called involutive algebra. So what I said is that the group algebra is an example of an involutive algebra. And a representation of an involutive algebra means that we have a map into the algebra of operators on a finite dimensional, in this situation, finite dimensional Hilbert space, so the space with a scalar product, and such that this map is compatible with the involution. So if the operator corresponding to this element coincides with the image of A, and this star is the usual conjugation on the space of operators in a Hilbert space. A finite dimensional Hilbert space, so there is no problem. Well, so this is the same. I will discuss it later, not today, in more detail. But just keep in mind that there is an equivalence, one can say formally, equivalence of categories. Representations of group, representations of algebra, unitary representations, star representations, or representations compatible with the involution. The next result is a very important and fundamental result, which says the following. This is the result about the structure of the group algebra as an algebra. So in words, which means that this algebra is a direct sum of matrix algebras. So more formally is as follows, more precisely. This algebra is isomorphic to the direct sum over the irreducibles of the matrix or operator algebra if you want, but here this is simply the algebra operators of on a finite dimensional space of so taken for each irreducible representations. So this is, if you take some basis in this space, this is exactly the matrix algebra. So the question, the result is that we have this an isomorphism. And moreover, this isomorphism is also compatible with the involution, because we have an involution here, but we have also the operator involution on each of these spaces. So this isomorphism is an isomorphism of involutive algebra 2. How to prove this? First of all, so the proof. First of all, we have a map. We have a map. We have a row in one side, which is pretty obvious. In what direction? In this one. Namely, given an element A, we assign to it the direct sum of its images. By the very definition of representation, this is an algebra morphism. And what next? So this is the first point. The next remark is that the dimensions are the same. Dimension of this is equal to the order of the group. And recall that this is the sum of dimensions of irreducible squared dimensions, irreducible representations, and this is the same as the sum of dimensions of these algebras. Okay, and this is the dimension of this object on the right-hand side. So we have an algebra morphism from this to this, and the dimensions are the same. So to complete the proof, we only need to show that the map is surjective. And this will be enough. And how to prove this? Let me recall the definition of the operator A psi eta. So assume that we fixed, say T is irreducible, and take two vectors from the representation space, and we assign to them an operator, which is as follows. Its action is a rank 1 operator acting on a vector x as follows. We take its scalar product with eta, and take it as a coefficient for psi. So this is rank 1. In this space. And the whole space is a linear span of such rank 1 operators. It's easy to see. So it's enough to prove that. So I will produce explicitly produce the element. So it's given T, maybe it's okay. So we produce an element given T and psi eta. For this data, I will produce immediately an element. It depends on T also, the group algebra, such that the image of this operator in the T component of this direct sum of algebras. So it will prove the fact that our map is onto. And what is this element? It turns out that we have to set as follows. Take the dimension, divide by the order of the group, take the sum over the group elements, take this, and the coefficient is as follows. We take the matrix element, but attention, this one. So first of all, we interchange the order psi and eta and take the bar conjugate function. So we have to check that it's indeed what we want. So check verification of fact that this is mapped onto. How to prove this? So let T prime is some irreducible representation. And let's compute. Take the image of these operators, of this element in the representation T prime, and take the matrix element. So X, Y are in the space of T prime. And let's compute it. So this is a direct computation from the very definition of this object. So what we get, right, as follows, and then the sum as before, and this, and now instead of this, we have to take a matrix, another matrix coefficient. Well, and now write this just an obvious transformation. Just to encode what is this. Just apply the definition of what is this matrix coefficient. In doing this, we get the following. T of G eta xi and T prime with G x y. And what we have? That we have now we can apply the orthogonality relation by orthogonality relation. We have first, if T prime is not equivalent to T, this is 0, because this is the scalar product of two matrix elements which correspond to different irreducible representations. So the result is 0. This is what we want, because we want to produce an element of group algebra which corresponds to a single component. Now assume that T prime is the same as T, and again by orthogonality relation, we get what we get, and now we want then this result applying the orthogonality relation gives us this is equal to x eta. We just to reduce this to the convenient form of orthogonality relation, we should imagine this as first and place this on the right. And then we get that the result is equal to the product like this one. And this is the same as this one. And this is the same by the very definition of this operator. This is the same as. So we have proved that T is equal to this one. This is for any x and y. So this implies that is exactly what we want. So this is a good result, very good result, very good. One consequence corollary is one of the possible proofs of a Burnside theorem. Burnside theorem, which means that the image of the group algebra in the space of operators is the whole this space. Some question? Sorry, I will try. Verbitsky. excuse me, isn't it's difficult to me to understand. I'm very sorry. Maybe discuss it later if there is some. I hope it's okay, but let me postpone this discussion. I'm sorry. So the image of a group algebra in an irreducible representation is the whole space of operators. So this is a very important result. This is not the only possible proof, but it's good to deduce this in this way. And one more important result is as follows. One more, I propose it as a problem to deduce the following corollary. So assume U is some representation, arbitrary representation, and T is irreducible. And then take A, maybe denote, better to say, right as well. With the following action. The sum, the character, and so this is an element of a group algebra. So this is the definition. And the claim is that in any representation, the image of this element is the projection, orthogonal projection onto the T isotypic component of U. I recall what is this. We take the primary decomposition. I recall it's unique decomposition on representations which are primary. That is direct sums of copies of one and the same irreducible representation. And it's useful to possess an operator which is built from the group elements and which is a projection onto a given component, which is called isotypic component. And this is...
Извините, пожалуйста.
Да.
Вот вследствие Бернсайда, Т это неприводимое представление или обычное?
Нет, это, конечно, неприводимое представление.
Сейчас, а что это значит образ групповой алгебры? Это есть... Просто это же, по сути, то же самое, что вы писали выше, нет? Что там это... И это не то.
Следствие. Значит, мы берем неприводимое представление, мы отправляем групповую алгебру в пространство представлений, получаем какое-то множество операторов, какую-то алгебру операторов в этом пространстве. И утверждение состоит в том, что это вся алгебра. Что это не может быть какая-то собственная подалгебра. Это верно, причем это очень важно, что это верно в случае, здесь очень важно, что у нас мы работаем над алгебраически замкнутым полем. Если бы, например, мы работали бы над полем вещественных чисел, рассматривали вещественные представления, то это неверно. У нас могут быть представления, которые неприводимы как вещественные представления, то есть у них нет, это представление действует в вещественном пространстве, и не имеет собственных инвариантных пространств, оно неприводимо, но это вовсе не означает, что образ, что линейная оболочка операторов представления заполняет всю алгебру операторов в этом пространстве. Это существенно, здесь существенно, что более алгебраически. Еще раз. Let me repeat. If we have an irreducible representation, take the linear span of the operator corresponding to the group elements, and what we get is the whole algebra of operators on this space. So this is the Burnside theorem. Is it okay again?
Да, спасибо большое.
So this is one of very fundamental results. And now, using the considerations that I tried to explain, we can build some elements of a group algebra with idempotence. Idempotence in the sense that they are self-adjoint. This element are self-adjoint. So, and they are idempotence, which means so in any representation, this is a projection. Projection is self-adjoint projection, or we can say orthogonal projections. Orthogonal projection on a subspace. And what is this subspace? It's always some isotypic components, exactly the isotypic components which corresponds to this given T. So I propose to prove this as an exercise. It's easy, but it's useful. And what next? I have some time. I want to discuss so all this is a very, very standard material. Now I want to discuss a material which is also standard, but maybe not so popular for the textbooks. So it's so this material, let's call it subalgebras. Subalgebras in the group algebra. What subalgebra I mean? So assume as above G is a finite group and H is a subgroup. And given a subgroup, we can assign to it an idempotent and self-adjoint idempotent. Let me denote it as epsilon sub H. And what is this? This is the formal we divide by the order of a group and take the sum of the group elements from the subgroup. One immediately verify that we have same relations as above. And what is the meaning of this? The idea is as follows. Okay, so given a representation T of G, the image of this specific element is exactly the projection, I mean orthogonal projection, onto the subspace. This is the subspace, the subspace of H invariant vectors. So just verify this, that when we apply H to any vector X, we get H invariant and vice versa. If you have an H invariant vectors, then applying to it this operator gives the same result. So this is a projection, and orthogonal projection. This is implied by the fact that it is not something like this, but orthogonal. It's a corollary of this fact. So this is easy. This is easy to see. And we assign to H, to any subgroup, a subalgebra. A subalgebra is this one. What is this? By the very definition, it is the set of elements in the group algebra with this form. This is a very standard construction for algebras. If we have some idempotent in an algebra, we can take if more generally. If A is algebra, epsilon is an idempotent, meaning epsilon square is this one, then this object is a subalgebra. So we apply this standard construction. Why? What is the meaning also? In the case we take exactly this specific idempotent. This object is precisely the set of H by invariant elements in the group algebra. What means by H invariant? Our group acts on the group algebra by right shifts and left shifts. And so we can speak about H invariant on the right or H invariance on the left. And this averaging, because this is an averaging operation, look at this. Once we take the product is the convolution, with this element on the right, we get a right invariant function, invariant with respect to this function. If we multiply on the left by this element, we get left invariant. If you do this on the left and on the right, then you get bi-invariant element. And this is a subalgebra. Now one has the following definition. One says that G and H is a Gelfand pair if this subalgebra, which is also denoted sometimes in this way, this is just a notation. Two slash bars here just symbolize that we have two-sided invariance. If this subalgebra is commutative, commutative. So this is the definition. Why it's important? This is so because of the following theorem. So assume GH is a Gelfand pair. Then it follows if T is irreducible, then the subspace of H invariance is either 0 or one dimension. So the subgroup is such that H invariants are at most one dimension. Sometimes it can be 0, no invariance. And if there is a vector which is H invariant, then this vector is unique up to a scalar. So this is some invariant of a representation. Very important. So we prove. So we take P is the image of our idempotent. So we know this is a projection. This is a projection, and namely, this is indeed a projection onto the subspace H invariant. So consider the map. We have a map. Of this algebra, which is the same as one. To the algebra of endomorphisms on this subspace. How it looks? And very simply, given A, we assign to it T of, which is the same as which is the same, just we use the definition as P, A, and we regard this as an operator on this subspace. So this is the usual thing. If we have some subspace and a projection of this subspace, then we can consider any operator of such a type, which is an operator on the initial space, but it is essentially the operator on this space because it has this form. Something here, 0, 0. Okay. But the next observation is, so this map A to P or A in our subalgebra is an algebra morphism. Between this subalgebra in the algebra of operators. But next, it is onto. It is surjective. Why? Very simple, because as A range over all algebra of all the whole group algebra, we apply the Burnside theorem. So these operators range over all operators in our space. And so writing P on the left on the right, we get all operators of this block form, 0, 0 here, and everything here. Okay. So this morphism is surjective. But this algebra is commutative by the definition of a Gelfand pair. This implies that this algebra is, if it is non-zero, so assume it's non-zero, so it's one dimension, because it is the algebra of all operators. It's commutative, so the space has dimension 1. This is important. Actually, I don't have time to prove the reverse claim, but actually, the inverse claim is also true. The inverse is also true. And we have only a few minutes. So, okay, I have to stop. I will discuss it the next time, but I would like only to produce some examples. Examples of Gelfand pairs. One example is as follows. Let n write this as a sum of two natural numbers and consider the symmetry group. I prefer to write it as follows. It contains the product of two symmetric groups. And I claim this is, we take this as G and H, we get a Gelfand pair. One more example actually related to this one is as follows. Take as G a group of general linear group of a finite field. And take as H the so-called maximal parabolic subgroup. This is the subgroup of matrices of such type. Everything, 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 and 0. And this is of size k, and this is of size n. Block matrices of this specific form, and this is also a Gelfand pair. And I would like some very imprecise remark is that these two cases are, these two pictures are similar. Because in a certain sense, this is a speculation. A symmetric group can be viewed as a, so informally, let me write it. Formally. I stress informally. Symmetric group can be written as GLN over the field with one element which does not exist. But actually, there is some parallelism between representation theory of GLN, the finite fields, and the symmetry group, which is manifested in many results. So such a subgroup, which is an instance of a Young subgroup, should be viewed as an analog of this parabolic subgroup. And indeed, if you want to write permutation matrix of such a form, we immediately get that this block should be zero for symmetric, for permutation matrices. And so we get exactly this subgroup. So this is, in a sense, parabolic. And some people even say this. This is a parabolic subgroup in the symmetrical. So I'm sorry, I don't have time. I cannot explain this. Let me postpone the discussion to the next lecture, and I will stop. Let me switch off the